Okay, so thanks, Max. So Max asked me to talk quite generally about aging clocks. So I'm going to talk a little bit about the clock we made, but it's not, specifically about our clock. It's more a little bit about thinking about building aging clocks and what they're good for. So, okay, it's a device for the measurement of time, of course. But broadly speaking, when we talk about a clock, what we talk about is a device that counts some sort of oscillation. So you have some sort of, repetitive event that you're counting. And here's an example of the thing that counts oscillations. What it counts in this case is the movement of the pendulum. And so that's what you use to get seconds or minutes. When we talk about aging, usually we're interested in years and days and years. So we count the rotations of the planet, put that in the calendar, and basically we call that the age. Now, those are chronological aging measures. And so, for instance, here you have an example of this where the tree has rings and the rings are seasonal, and so you can count the number of years that the tree has stood somewhere and has existed. Now, those are wall clock or calendar clock or chronological age measures. However, when we talk about biological clocks, we mean something very different. So the question today is, what are aging clocks? What's biological age? And how do we measure this? Okay, so what is the difference between chronological age and biological age? If you're interested in biological age, you're going to eventually come across this gentleman, which is Gompertz. He was a mathematician and actuary. And he figured out that the risk of dying increases exponentially with the amount of time that an animal or human exists. So what that means is that the mortality, the risk of dying in any 1 year, increases exponentially with age. Now, here's an example of this. For humans, you might start out at an age of 10 with about a 1 in 10,000 chance of dying any 1 year. And then in humans, the doubling time for this, that is the characteristic time constants with which the risk doubles, is about 8 years. So after about 40 years, or at age 40, you have a risk of 1 in 600 of dying every 1 year, at 60 of 1 in 200 or 100, and at 80 of about 1 in 20. So this is an exponential risk increase, and it really runs away from you quite quickly. Eventually, it just becomes essentially 1. Now, the important thing is that if you just made a small difference to this doubling time, if you change doubling time from 8 years to 10 years, you would make quite a lot of difference to the risk of dying that you have by the time you reach old ages. So for instance, if you turned the mortality rate doubling time from once every 8 years into 1 every 10 years, you essentially would get the blue curve, which means that by the time you're 80 years old, you would essentially have the same risk of dying as a 60-year-old would have under normal aging. So this is basically just a 25% change in aging rate, and it has quite dramatic impact. For comparison, curing all cancers would only add about 3 years to life expectancy. So this would be much more dramatic than curing all of cancer. Now, an important thing here is that you might think, oh, okay, but I don't want to be old for longer. This is just mortality. But of course, you're not dying of some magic old age death where you fall asleep in your bed. You're dying of exactly those diseases that we have been talking about all day. You die of cardiovascular disease, cancer, kidney failure, infections, falls. You might have neurodegeneration. All of these things follow the same aging trajectory. So what we're talking about here is delaying all of these diseases at once if we could do it. Now, how do we know that that's even possible? I mean, I'm saying, okay, let's just make it 25% slower. That's like a nice idea. But how do you know it can be done? And, well, the truth is that we know that mortality can be modified by lots of factors. So we know diet and lifestyle does this in model organisms, but also with GWAS in humans, we know there's genetics, mutations, SNPs that can do this. You can easily change this aging rate by selection experiments in model organisms, and you can use gene therapy. And increasingly, we know that that's true with drugs. We can use drugs to change age-dependent mortality and extend lifespan. We know this in model organisms like nematode worms, which I use in my lab, and fruit flies in mice, and increasingly we realize that the same is true in people. And I'm going to show you an example from my lab in nematode worms just to show some of my data. So this is normal lifespan for these worms. They live 30 days. So on the x-axis you have time, on the y-axis survival. Everybody starts out alive, and after about a month they're all dead. And then you can take an adult animal that's already reproductively active and treat them with a drug combination, and you can get lifespan curve that looks like this. So this is an adult animal, wild type, and the only difference is that you subject it to some drug treatment regime and you get this sort of extension of lifespan. So obviously, you made quite a lot of difference to the risk of dying as a function of age, and so you modified aging. It's not difficult to do that in the lab. We do it all the time. We haven't done it in people yet, but we've done it in almost any other organism that we can you quickly test. Okay, so just to show you that they're not old for longer, these are the same guys. On the right, you have the animals that are treated. On the left, you have the animals that are untreated, and they're the same age. So that's what they look like. On the left is how nature intended, dead and dying and decrepit. And on the right, you have the treated animals, and they are much healthier for much longer. Okay, so the point here is that we can do this, but how can we test this in humans? Because you can't do this experiments in humans. You can't treat people for 80 years and then see whether it helps and then change the treatment protocol. Not only is it unethical, but it's also just very slow and expensive. And so that's where aging clocks come in. This is just trying to say that humans also don't age at the same rate. So you look at these two guys, they're the same age. They used to look quite similar when they were young, but Tom Cruise has obviously aged much more successfully in many ways than Val Kilmer has. And so there's a point to be made that humans also age at different rates, depending on the modifiable lifestyle factors already. Okay, so how do we do this? How do we make a clock? Well, you start out with some sort of features. Just now I showed you some facial figures, and you already can tell which one is more of the two is aging more successfully. And you probably have heard of epigenetic clocks. So epigenetics is one type of feature space, a set of things about an organism that I can use to measure. We heard about glycan age earlier. That's another type of feature space. So we can use different things. But the important thing to realize is that all of these parameters are related to each other. Living things are highly connected, correlated networks. And you modify one thing, you will always modify other things as well. So for instance, DNA methylation changes transcription. If you make differences in transcription, you will get differences in metabolites. If you make differences in metabolites, you would get differences in metabolism and how the system works, post-translational modifications. This will change cell fate, organ function, and eventually visible phenotypes of the organism. So what this means is I can watch the aging trajectory of an animal at almost any type of feature space I want. I can extract aging patterns from there and watch the aging in that particular feature space that I've picked. I can make a clock out of almost any omics measurement is what that means. Now, when I do that, I take some sort of set of features, epigenetic markers or clinical biomarkers or glycans, and then I combine this with ideally data on mortality, because what I'm trying to do is modify, aging trajectory, which is defined by mortality. And then I do some math and some computer modeling or machine learning nowadays, and I get a model that will predict my mortality rate, health parameters, and in other words, will predict the biological age. Because what I'm saying is, if your mortality of dying is that of a 25-year-old, you're 25 years old. Okay, so I'll give you an example where we have done this just as a proof of principle. This uses the National Health and Nutrition Examination Survey in the US. It uses data on demographics, on some questionnaire data, for instance, on smoking and diet, medical examination, and some biomarkers. And it uses these things to then use the known follow-up. There's a 20-year follow-up in this cohort. They were recruited in 99, 2000. And then basically make a model that predicts future mortality and turns this mortality into biological age. So that's what that data set looks like. And what you have here is on the x-axis, the chronological age, so the calendar age of these people, and the y-axis, the predicted biological age. And if you look, there are lots of people who are older than their chronological age, because it's much easier to mess things up than to make them better, right? It's much easier to have a higher risk of dying than a lower risk. But there are also people who age much more successfully than their chronological, or they're younger by the risk than their chronological age would suggest. And so we can use this to then look whether this clock has predictive power. So we take an age bin here for around 70, from 65 to 75, and we take the best ages and the worst ages, and we look what actually happened to them historically. And this is data set not used for testing, for training. This is a testing set, separate cohort. And what you can see is that the people that are above, that means that they have a biological age larger than their chronological age, are surviving quite badly over the next 20 years. So this is a 20-year follow-up, and less than 20% of the worst top 20% bio-age survive this follow-up period. So 80% of them die. by comparison, if you take the most successful ages, then 75, 80% of those survive to the end of the follow-up. So this is quite a powerful predictor of future mortality. Now, this is relatively easy because these things are all known to related to disease, things like cholesterol and blood pressure and resting heart rate and BMI and those things. So it's quite easy to interpret what this means and where it's coming from. This is, I had to take one slide out. This is a feature space. So this is a projection of all the people where they are biologically. So this is like 160 parameters, but here we flatten them into just 2 and put them in clusters. So people that together, close to each other, are biologically similar in this feature space. And here we have the survival for these features, and I'll run you quickly through the clusters, through the sets of people. So we have in the back here, the red guys, they have specific diseases. So from the data, we know that they're actually sick. And there's a quote that happy families are happy in the same way, and unhappy families are unhappy in their private ways. And that's true here. Being diseased makes you very different from other people that are healthy and also from other people that are diseased because they have different things wrong with them. So there's a large spread of those people, and their survival in the red here is very short. So very few of them survive because they start out 20 years ago being sick. And then we have the metabolic, the orange cluster, metabolic cardiovascular disease cluster. And these people are classically overweight, obese, metabolic disease, high cholesterol, high blood pressure, and they die early. We also have a multimorbid cluster, which are people of lower education, use the healthcare system less successfully, do not get screening and follow-up, and have various things wrong with them. That's why we call it multimorbid, but they're not overweight on average, but they also die young. And then we have in the middle here a healthy aging cluster, the green guys, and they survive by far the best. Now, what's the use of looking at it this way? And I think one of the important things for aging clocks is that they're navigational aids. So you have disease markers, and you can do a test whether you have a given disease, kidney failure or cancer or heart disease, but that's a binary response. You say, okay, you're not having the disease, or you're having the disease, and so there's limited advantage other than treating for the respective disease once you have it. You can also have markers for either cardiovascular disease or some of those other causes of death. And so you can have, for instance, a cardiovascular disease marker and say, what's your risk of having a heart attack? And those are useful if that's what you're eventually dying of, but you can have a low risk of cardiovascular disease and still be unwell and not survive very long. So you have to screen for every possible thing that might at some point affect you all the time in order to catch them. The nice thing about an aging clock is, in theory, it defines an area where the optimal aging trajectory lies. So you can say you're aging well, you're lower than your biological age, you're okay in every domain. And that's an interesting way of thinking about it. It's a normative target to aspire to. And I think that's a useful feature of biological aging clocks. To show you that last point again, here you have the thing I showed you before, and there are 2 extra curves in it. The lower red curve shows high cardiovascular disease risk. And as you can see, the clock agrees completely. The clock is a bit better at picking people up that will live short, but many of them have high cardiovascular disease risk. It's a classical ASCVD marker used in the clinic. And people who have a high risk of cardiovascular disease, the clock calls them old and they die young. But on the top here, you get an opposite thing. People with very low cardiovascular disease risk aren't all surviving as well as people who have low bio-age. So in other words, the clock is much better at picking up people that are going to do very well than just saying you have a low cardiovascular risk. So these healthy people here are more healthy than just not having cardiovascular disease risk, and that's a useful feature of aging clocks to sort of have a normative target. Okay. You can also then look at what the loadings for this are. In other words, you can investigate what are the features that are driving these directions that I show you. What does it mean to go from green to yellow or from green to orange? And you can, of course, identify risk markers and identify mechanisms. So you can figure out what is actually happening to the people. And if you're interested, there's a paper where we dig into this and identify some failure modes and drugs that could be used to intervene. So this is what this shows. To make a long story short, there's a high degree of inflammation and inflammatory disease, as everybody is expecting, but it comes out very nicely, shows markers of inflammation are elevated if you go away from the healthy cluster, no matter whether you go towards the more obese cardiovascular side or the frail side of the cluster, and these are modifiable parameters, so there are interventions you can pick to make this better. So my summary at the end is, and that's about aging clocks in general, not just our clock, is that aging clocks are very useful, I think, one, to provide personalized risk estimates. For intervention testing, of course, if you can do a clock with high precision, you might follow people up for only 2 years, and if they're only aged 1 year in those 2 years, then the intervention has worked. It's very different from following people up for 25 years and paying for that follow-up. They can give normative targets. You can say, what does healthy aging look like? What is the best possible place to be in your biological feature space? They can be used to investigate mechanisms of aging. You can figure out what distinguishes healthy from non-healthy aging, what are the events and the processes that are driven by this. And of course, they could ultimately inform treatment strategies. You can identify interventions that you can use. And by the way, in our case, those are not like complicated biotech interventions. This is basically just early and proactive control of existing risk markers. So the idea is more earlier and more proactively intervene against processes we already have identified as detrimental to long-term health. And so this is my little summary on what aging clocks can do for you. And again, I used our clock because I have the data and the figures, and I don't have to steal somebody else's. Plenty of clocks, everybody's working on this. And I think if we make mortality the thing we all compare, then eventually all these clocks will probably give us very similar answers, just to figure out which one works the best. So thank you very much, and if you have any questions.